Now, we will move to the keynote speech. The first remark is by the Professor Stephen Chu. He will give us the lecture by the web. Stephen, are you in the web now? Okay, I haven't seen you for a long time. You are the Secretary of Energy when I was the Executive Director of the IEA. I am really admire your great wisdom in the energy sector and science. The floor is yours. Please go ahead.
All right, I'm not sure if you can hear me, and I will try to run this PowerPoint from my end because the backward sound is a little bit funny. Anyway, it's a pleasure to be here. I have only 10, 12 minutes, 15 minutes to talk. And so I thought I'd give you a very quick synopsis of the innovations that we need, that we don't have the technology, so we can focus on the things we need rather than things which are in good shape. So let me begin. I cannot seem to move this. This is really odd. So you need to go to the next slide. Am I running the show or are you running the show? Okay, so the cost of renewable energy is coming down dramatically. This is a chart of some of the costs from 1983 to 2021, and you see that solar, wind, photovoltaic, onshore wind coming down dramatically. Next slide. This is a little crazy because I was told you guys I wanted to run the slides myself. Please, next slide. Can I run the slides myself? Hello? Great, thank you. So the full cost of renewable energy includes not only the cost of renewable energy, but the backup generation capacity, energy storage, and enhanced transmission and distribution system. When renewable energy is 10, 20, 30% of the total energy, it doesn't matter. When it goes to 50, 60, 70%, it matters a lot. And we also need clean energy for process heat to be used in industry to make steel, cement, chemicals, plastics, and other materials. So energy storage becomes a key factor in renewable energy. At the very short time scale on the lower left-hand corner over here, where we see laser pointer, where we see flywheels. This is for short-term stability to take care of the very high-frequency noise that comes from intermittent solar and clouds and things like that. We have batteries, and then going further up to longer and longer storage, and this is time in storage from compressed air, pumped hydro, which Japan for a while was the leader in pumped hydro, is the time-honored energy storage mechanism responsible for 95% of electrical storage. But we'll need more. And there's a lot of attention now being placed on what we call chemical storage, but without the overhead of the batteries. And this would mean hydrogen, ammonia, methanol, green methane, and so on. So let me talk very briefly about hydrogen. It comes in different colors. Gray hydrogen is where you take natural gas out of the ground, you can convert it into hydrogen and CO2 as the end result, and you vent the CO2. And so in terms of CO2 emissions, it's no better than just burning natural gas. It's the lowest cost hydrogen. Then there's what we call blue hydrogen. You take natural gas out of the ground, you convert it into hydrogen and CO2, you capture the CO2 and you sequester. It's slightly more expensive, and for the first decade or two, blue hydrogen will be the dominant thing, but in the end, we will need green hydrogen, which now costs anywhere from $4 to $6 a kilogram. blue hydrogen has a problem. And it can only be a 1, maybe 2-decade solution, because when you drill for natural gas, you disturb the ground, and between 2 and 6% of the natural gas leaks out of the gas fields, and that escapes into the atmosphere. And so it's a huge problem. But in order to make green hydrogen cheaper, it can't use the precious metal catalyst we now use, and it really has to come down by a factor of 2 or 3. There's a problem. Hydrogen is very leaky, and we don't have a good means of remotely sensing if there's a hydrogen leak, and that has to be developed. Until there was remote sensing, we didn't know how much natural gas was leaking out of the ground and out of pipelines. So that's another technology that has to be developed. But having all these things of hydrogen, I should say that green hydrogen could be used to decarbonize the steelmaking process, the so-called coking process. It can be used in chemicals and plastics, first starting with fossil oil and natural gas, but in the end, it can be the replacement for those things we now use to make chemicals, fertilizer, and sustainable aviation fuel. So hydrogen has to be part of the solution. Now, if I ask countries like Japan, South Korea, and other places, if you take oil, let's say in the Middle East or in the United States or wherever, and you ship it halfway around the world to Japan, what would be the cost in terms of how many dollars per gallon for shipping crude oil halfway around the world and storing it? And it turns out that it only adds 2 cents per gallon of gasoline. So I'm telling you this because these tankers, these super tankers, are extremely efficient at transporting energy halfway around the world. This is very important. So you should think of oil tankers as an intercontinental energy transmission line. So going back to how do you get green energy from places where it's abundant, where there's a lot of solar, where there's a lot of hydro, where there's a lot of everything, how do you get that energy into places where you don't have that? And the answer is you use tankers. Now, I want to say that chemical batteries, I've lost my picture of chemical batteries, but never mind that. I had a beautiful picture of a Japanese tanker, and somehow that version didn't come through. But anyway, so the point of this, I'm going to go back to this, is that Japan is now in the business of trying to get super tankers that can transport ammonia, methanol, or liquefied green natural gas, because it's these transport vessels that can go across oceans at a very low cost. And so that's a big effort, and this is all exploratory. I know Japan is seeking to take energy from, for example, Canada and the United States on the West Coast, where you have abundant, cheap green energy, turn it into methanol or ammonia and ship it across. But it has to be done economically. Let me talk a little bit about energy storage. Chemical batteries have made remarkable progress. If you look at this graph on the left-hand side, you have energy density per unit weight, watts per kilogram, or energy density per unit volume. And these are the various battery technologies. This little blue circle is a reference of the Tesla batteries. And within 5-10 years maximum, the energy density will essentially double. And I say this for 2 respects. I'm doing battery research, but I'm also on the board of directors of a battery company. And this battery company is shipping test batteries to automobile manufacturers today with these very high energy densities. There's other very good news. The good news is the cost of lithium-ion batteries for automobiles has plummeted. And so this is, again, what's called a learning curve. On the x-axis is the amount of batteries put into production and into service going by powers of 10. And on the y-axis, going by powers of 10, 1,000, 10,000, and so on, you have the cost. And once you start making a lot of batteries and you go down in production cost and experience, the batteries are plunging. The great news, in the year 2000, lithium-ion batteries were exorbitantly expensive, $2,000 a kilowatt hour. In 20 years, the price dropped by a factor of 20. In another 10 years, it's highly likely that the price will drop by another factor of 2. So that means vehicles, electric vehicles that can go 300 miles in one sitting will cost no more than an internal combustion engine car. So that's all great news. What do we need? Well, this cost curve has to go down because we need better sources of lithium. I and others are working on methods to extract lithium from seawater so it can be accessible to many, many countries. And if this is successful, then lithium batteries for automobiles will have enough lithium for total electrification of personal vehicles for decades, and actually hundreds of years. However, there's another issue, and that is when we talk about utility scale batteries, there's not enough lithium for utility scale batteries because batteries that store electricity for electrification of a country, there have to be 1,000 times more batteries. So all of a sudden, for that, lithium is going to be too expensive. Similarly, you need the batteries to be safe. There's large amounts of energy storage. And so there's a recognition that instead of the usual electrolytes, which can catch fire, for utility scale storage, they have to be water-based. And so there's active research going on, but we don't have this technology in hand. And so even with utility scale batteries that would be cost effective in 10 or 20 years, not today, you still need some compact turn-on sources of energy, and there's only 3 choices in the technology we have today: coal burning, natural gas, or nuclear power. So let me spend 1 minute talking about the relative benefits of these sources of energy. And the most relevant thing for the public is how many people die from using coal, brown coal or black coal, per unit of electricity generated, burning oil for electricity, burning biomass, wood pellets for electricity, natural gas, hydropower. So these are the number of deaths per unit energy. And you see that coal is by far and away the leader. It's because of the air pollution, the particulate matter, very, very deadly stuff, mercury as well, followed by oil because of particulate matter and NOx and things. Here's biomass. Where's nuclear? Nuclear is down here. Nuclear is considerably safer than hydropower because occasionally dams burst and people drown. Nuclear is safer than wind because people can fall from a wind tower servicing them. So if you include all the nuclear accidents in Fukushima, Chernobyl, you name it, and of all the energy generated, it turns out nuclear is somewhere between wind and solar, but wind, solar, and nuclear are really not that dangerous. Also, there's newer technologies that can actually sequester the material very safely using drilling technology. As an example, there's small compact nuclear reactors. That whole thing could be made to fit on a truck. This is an example of a company called NuScale is designing these things. And then it can be fueled in 5 or 10 years, and after its service life is done, you can take the whole thing and put it in a borehole and bury it as a unit. There's a new economics regarding this because these small modular reactors would be used for standby power, maybe 5 or 10% of the time, but they're expensive. They're high, what we call CapEx. So the new economics is these are compact, carbon-free sources of energy. 5% of the time, 10% of the time, they supply standby electricity. The rest of the time, they can be used to make hydrogen or desalinate water. And this new economics, if you make 1,000 of these in a factory and ship them all over the world, can make nuclear energy much more viable than using natural gas, capturing the CO2 and burying that underground. The amount of material for natural gas sequestration in nuclear is orders of magnitude. And so this is actually a safer thing. In the end, as I said before, the challenge is we want to take CO2, water, use clean energy, and start to make hydrogen, CO, and hydrocarbon fuels. And so, and these liquid hydrogen carriers, let's say ammonia organic carriers and methanol, I already spoke of. This is the thing slide I went, there's a little sequence, now I found it. Mitsubishi MOL is beginning to look at ammonia transport in Japan, South Korea. And the reason is you want to put these on the tankers to ship methanol, ammonia, whatever. Okay, given all that, given all these technologies we need, there's also a recognition that we will exceed 450 parts per million CO2. We will exceed probably 500, even 550. So you have to capture greenhouse gas at the sources, at steel plants, cement plants, everything else. But this is necessary, and we actually have to capture CO2 from the atmosphere. What's the cost goal? Well, if you can do it for $60 a ton from natural gas plants or steel plants, great. Less than $100 a ton from direct air capture, great. But in the end, I will turn back to what nature has given us. And with this ending slide, I will say that plants we plant for food, corn, wheat, rice, you name it. Those crops capture 10 to 20 billion tons of CO2 a year. The total human emissions of both CO2, methane, nitrous oxide is about 52 billion tons a year. If you could take the leftover residue plants, compact it, dry it out, so bacteria, microbes, fungi don't grow, then it turns out that this is a solar-powered capture of CO2 from the atmosphere that nature has given us. And as people begin to look at that, this may be able to capture 10 gigatons a year that could be in low-tech storage, and it's safe. And so people are beginning to think maybe this is a way to capture CO2 as opposed to all these exotic ways. So I'm going to end here and just summarize by saying these are some of the technologies that we have to develop. We don't have them in-house. EV batteries, good. Wind, solar, great. But in the end, these are the things scientists, engineers, and technologies have to meet these challenges and overcome. And with that, I will stop and end. Thank you.
Thank you very much, Stephen.
And I will stop sharing.
Yeah, very good overview. And as always, I'm very much impressed with what Stephen told us as a big picture of covering all the relevant technologies and ways how we can make carbon neutral. I think, can I ask you the question? I mean, are you hearing us? I'm afraid not. Okay, well, then thank you very much, Stephen, for joining us as a keynote speaker and give us very good insight for the future work of ICEF. Thank you. Well, let's move to the next speaker as a keynote. He is Dr. Noguchi Soichi, our very prominent and famous astronaut some time ago, and he will tell us from the view from the space. Dr. Noguchi, please come to the podium and take the floor.
Thank you, Tanaka-san. Distinguished guests, good morning. My name is Soichi Noguchi. I'm an astronaut and I'm Chief Executive Fellow of IISc. Well, this morning when I talked to Tanaka-san, he said I have to end by 10 a.m. Now it's 10:05. So my first innovation is travel back in time. Anyway, I'm going to do it really quick. Well, my first question is, what does cool Earth mean to you? Like many things in our life, it depends on the point of view. My point of view, cool Earth means the blue marble, which I saw from the International Space Station. I was fortunate enough to fly to the space station 3 times and watched Earth rotating beneath us 340 days. And Earth was beautiful. Well, astronaut is cool. Flying to space is cooler. But the coolest is the view from space, the Earth. It's beautiful, it's breathtakingly beautiful, it's dynamic, and it's full of life. Well, the reality is, however, Earth is not cool anymore, and we all know that's the hot topic. I can give you a couple of the recent numbers. Here's a recap. First thing is, the latest edition of the World Economic Forum Global Risk Report this year, 2023. The top 6 out of 10, the global risks are environment-related, such as failure to address climate change and biodiversity loss. That tells us that environment-related issues are far more important than geopolitical issues like Ukraine or the global south, or the cybersecurity related issues. So we can say that environmental issues are one of the most important topics that politicians, economists, and academicians around the world are focusing on, at least at the World Economic Forum level. Also, the United Nations Secretary General Antonio Guterres recently said that the era of global warming has come to an end, and the era of global boiling has arrived. In fact, we all know that Tokyo just suffered the hottest summer in 126 years. 126 years, it's almost samurai era, and we had the hottest summer. The other example is the recent wildfire in Hawaii. It's said to be caused by drought, strong winds, and other unusual climate changes in those regions. Although the exact cause of the fire is still unknown, but weather conditions previously considered abnormal now became the new normal. Dealing with environmental issues, however, involves more than just dealing with extreme weather. These many issues that need to be addressed, such as mitigation and adaptation, to attack the climate change and procurement of the resources and the conversion of the conservation of biodiversity. Obviously, those discussions sometimes tend to take a negative turn amid the political atmosphere amongst politicians, business people, and environmental activists. And sometimes we have to compromise to solve short-term issues in the sake of the long-term issues. How should we deal with those various issues pertaining to the environment? I believe that technical approach to solving environmental issues entails 3 aspects of visualization, analysis, and prescription. I think these solutions can be carried out under several categories. Let's take carbon neutrality as example. We should visualize the emission of invisible greenhouse gases, GHG, such as CO2, and analyze the sources of these emissions, as well as corporate and individual activities causing them. Then once we identify the source of emissions and activities that cause them, we should respond to reduce emissions by making full use of information and communication technology, ICT, and artificial intelligence, AI. As such, visualization, analysis, and prescription constitute a positive cycle for addressing environmental issues. I believe that three perspectives of visualization, analysis, and prescription are not only relevant for achieving carbon neutrality, but also for solving other issues such as biodiversity. In particular, with regard to prescription, it is necessary to formulate measures for financing and creating new rules to ensure international fairness, which are very critical in implementing prescriptions. ICEF is a venue where industry, government, and academia leaders from around the world gather to promote innovation and explore solutions based on innovation, which is a key to combating global boiling. I believe that potential for innovation in science and technology, including ICT and AI, in the areas of visualization, analysis, and prescription. As an engineer myself, I have a keen interest in the development of innovations to solve global boiling and other environmental issues, and have high expectation for it. Intergovernmental Panel for Climate Change, IPCC, asserts on their report that there's no doubt that the impact of human activities had led to the warming of the atmosphere, oceans, and the land. It also forecasts that global boiling would continue. The environment that deteriorated at the hands of mankind must be fixed by mankind. I hope that wisdom and innovation of mankind will be able to overturn those IPCC predictions in a positive way. Finally, I would like to conclude by reiterating 2 points. Number one, the passion of everyone gathered here is essential to solving environmental issues. Number two, our business and actions have a potential to change the world. Thank you for your attention. ありがとうございました。
Thank you very much, Noguchi-san. May I ask one question? Because
Yes,
this
sir.
is a rare opportunity to ask
Yes,
a
sir.
question to the astronauts, so I don't want to waste it. When you see the Earth from the space, you called it very cool Earth, maybe, but now it's a boiling Earth, may somebody say. Do you think there's some discussion that the Earth is coming close to the planetary boundary in terms of the climate or food or health or water, biodiversity? Do you think the tipping point, some of the index shows the tipping points for these planetary boundaries, we are already moving on above that tipping point. Do you think this kind of argument is necessary, and should ICEF discuss with this kind of issue?
Tanaka, thank you very much for the questions. That's very important. Obviously, when you see the Earth from space, one thing is really clear: we are resource limited, and we all know that. But you see that there's one ball, one blue marble that contains everything, and those the limited resources we have to conserve. And the biodiversity is one thing, water, agriculture, CO2, temperature, everything. So everything is resource limited. And well, I told you I was fortunate to fly 3 times over 15 years. And during those 15 years, I don't see huge changes. But yeah, if you see anything change, and visibly change in 15 years, that's a real issue, because we're talking about 4 billion years. And now, if something changes in 15 years, that's a huge issue. So I don't see the color change. I do not see the water boiling. But there's many scientific data shows the amount of ice in the polar region decreased by historical rate, or the temperature in the southern oceans is up in an irreversible manner. So obviously we have to keep in mind that the resource is definitely limited, and we have to monitor the slightest change, because that will definitely accumulate and cause a huge change. That's where the ICT and I comes into play. Thank you so much.
Thank you very much, Dr. Noguchi. Please join me.